and it's going to prepare us for the lab that we're doing tomorrow. It's all dealing with percentage compositions. Maybe. Oh, spinning rainbow of doom. There we go. So, percentage composition is the part divided by the whole, and then multiplied by 100. And here's our first problem. We're going to determine the percentage of hydrogen in water. We've got a big area there to do that. So what we need to do is look at the masses. Oh dear. Board just worked for me today. There we go. We need to look at the masses and the compound. So water is also dihydrogen monoxide, so H2O. So I have 2 hydrogens and 1 oxygen. So those subscripts there. So if I need to know the masses of each, I know that my hydrogen contributes 2 times the mass of hydrogen, which if you look on your periodic table is 1.01, and I get 2.02. Oxygen, there's just one of them, and it is 16.00. My total mass is the sum of these values at 18.02. Well, now if I'm looking just for the percentage of hydrogen in the water, I do part over whole. So I have 2.02. We will at the very end. 2.02 divided by 18.02 multiplied by 100. And with 3 sig figs, because that's my lowest number of sig figs, I get 11.2%. So 11.2% of water by mass is hydrogen. The rest of it's oxygen, which makes a lot of sense because oxygen is much bigger than hydrogen. What questions do you have so far? Yeah, Nikki.
When we're doing this, you want us to just round it up a bit, please?
I want you to look at your lowest number of sig figs and the values that you have to start with, which here it's 3. Good question. Other questions? So the empirical formula is what you're going to be determining in the lab tomorrow. It is the most simple whole number ratio of the elements within a compound. Again, this is what we're doing in the lab tomorrow. And how we do it is we calculate the number of moles of each atom within the molecule. So we'll measure out mass, then calculate moles, and then we'll find the most simple whole number ratio between those numbers. So these would be 2 good flashcards here. 1, what does empirical formula mean? That's the first bullet point. And then 2, a second flashcard would be how you do it. Yes. Okay. Let's take a look at our first example here. This part's already written down for you, but now we have to figure out how to do the rest of it. So we have copper oxide, and we know how much total we have of the copper oxide, and we know how much of just the copper we have. We need to determine the empirical formula. So one of the things that we have to do right off the bat is figure out how much oxygen we have. So given this data, how would I determine how much oxygen I have? Yeah, I would subtract, absolutely. So I have 2.476 minus 2.199. I would subtract the mass of the copper from the mass of the total to give my mass of oxygen. Now I'm doing subtraction, so my rules for sig figs for subtraction are the least number of digits after the decimal point. So each of these have 3 digits after the decimal point, so my final answer will have 3 digits after the decimal point. And what do we get? 0.277, excellent. That is my grams of oxygen. So I need to convert to moles, which we did early on in the school year. We're seeing it again here. So I take my grams of copper, we'll do that one first. So I start with my given, and I am going to convert to moles. Where would I get a molar mass? Where would I look to figure out the molar mass of something? Yes, thank you, the periodic table, good. So I look at my periodic table at copper, and 63.55 grams for every 1 mole. Would my grams, my 63.55, go on the top or the bottom? Bottom, absolutely, because then I'll be able to cancel it out. So 63.55 grams of Cu for every 1 mole of Cu is the other part of my ratio, so it goes on top. Yeah, Nikki.
Wait, why isn't it 546
Because the periodic table that I was looking at didn't have precise enough numbers. So I'm just rolling with what I got. Thank you. Yeah, the one that we have in this room is much more precise than the one that I had previously. Okay, which unit cancels out? Grams, absolutely. I'm going to be left with moles of Cu, which is good because that's what I'm looking for. So I take 2.199 divided by 63.55. I'm going to have 4 significant figures. What do we get? Anyone? Bueller. 0, 3, 4, 6. Did it give a number after the 6? What is it? Another 0? Okay, good, thank you. So, significant figures, if I need 4 of them, these are my 4 significant figures. These 2 zeros don't count as significant. We're remembering our 0 rules. So my answer is 0.03460 moles of Cu. Thank you. Okay, now I need to figure out my moles of my oxygen. So I'm going to start out with the value that I already calculated. This is my contribution of oxygen. So I have 0.277 grams of oxygen. And I look at my periodic table, and I find the mass, which will round it from what it is on this gigantic periodic table. We have 1 mole of oxygen on top, and on the bottom, 16.0 grams of oxygen. So 3 sig figs, what number do we get?
0.0173.
Thank you. 0.0173 moles of oxygen. Excellent. Thank you. Okay, now I need the most simple ratio. So what I'm going to do is divide each by our smallest number. So my ratio of oxygen is just going to be 1, because I'll take 0.0173 divided by 0.0173. My copper, I'm going to actually calculate out, it's 0.0346 divided by 0.0173. What do we get?
Where did you get to 0.173?
That is my moles of oxygen, which is my lowest moles. 2. So my ratio of oxygen to copper is 1 to 2. Now I can figure out that I must have Cu. Why did I just write that? Oh, that's what it is. Okay, Cu2. Oh. So if I were to name this, how would I name it? Go ahead, Katie.
Maybe copper 135.
Very close. Evan? Nope, not quite. Karsten. Copper 1. So this 2 came from the oxygen, which is good because oxygen is always a 2 negative, which means the copper was a 1. So copper, Roman numeral 1, oxide. Excellent. Yeah.
How did you get the oxygen being 1?
Because we took the lowest number of moles, which was 0.0173, and divided by that. Good question. Any other questions before we move along? Yes, Nikki. It is a transition metal, so I need to know the charge of it. Well, the charge was originally crisscrossed here, so I reverse crisscrossed to figure out what the charge of each of them were to start with. Oxygen was originally a 2 negative, which makes sense because that's where it is on the periodic table. And since nothing is behind the oxygen, when that crosses up, that must mean it's a 1 positive. So copper 1 oxide. Awesome. Yep. Yep, so I took each of the values, so the oxygen value and the copper value, divided by my smallest one, which was the oxygen value. So you'll always end up with 1 equaling 1. One of them equaling 1. Yeah. It should. It should. If it does not, like if you get a, bless you, 2.5 to 1, then we're going to have to multiply each of them by 2 to get our lowest value, which would be 2 to 5. Sometimes that'll happen, but it'll be nice, easy numbers to work with. Good question. Okay. Okay, when we are in the lab, like tomorrow, empirical actually comes from the word experimental. So one possibility we could have in the lab is that we're going to convert an element to the compound and then compare the weights. Or our second possibility is we could decompose a compound so that only one of the elements remains. And we do the same sort of thing if we need to figure out the formula of a hydrated salt, which is a big year 2 project for us, if you take that 3rd semester. Third possibility, we can burn an organic substance in excess oxygen to find out how much carbon dioxide is formed. It's written down for you already on the back of the page. You can see we're going to do another big example here. There's kind of a lot of writing, so you'll want to write small if possible. That looks like most of the pens. So, our example, we have an organic compound that contains 60% carbon, 4.48% hydrogen, and 35.52% oxygen, and we need to determine the empirical formula of this compound. So, first thing we need to do, this is odd because it's in percentages. We can't use them that way. We need to know what they are in mass, in grams, first. Okay, they're finally loaded. So, whenever you see a problem with percentages like this, you are going to assume that we have 100 grams. It's going to make life much easier for us because now we have 60.00 grams of oxygen, 4.48 grams of hydrogen, and 35.52 grams of, oops, I wrote down oxygen there, sorry, that was carbon for 60. Oxygen is 35.52.
So on the test, will we sometimes get us formulas, problems like that where it seems to be
Yes. Yes, in your review sheet, the last question on your review is like that. Okay. So now that I've assumed my 100 grams, what's my first step? You can look back. It's okay to look back. I think I heard somebody say it. We convert to moles. So, step 1, convert to moles. So, I have 60.00 grams of carbon. I'm going to look at the periodic table and I'll see that my molar mass of carbon is 12.01 grams per mole. So, every 1 mole of carbon contains 12.01 grams of carbon. I'm going to keep writing out the next steps. So my next one, 4.48 grams of hydrogen. Every 1 mole of hydrogen contains 1.01 grams of hydrogen from my periodic table. And then finally, my oxygen, 35.52 grams of oxygen. I have 1 mole of oxygen for every 16.00 grams of oxygen. And now I can calculate them all out.
I think the bottom is
2.22. Sounds good.
the top one is 4.99.
4.99. Let's see. Oop, we should be looking at sig figs. So, 2.22 works for that one because I wrote an extra sig fig that I didn't need. Oop. Okay. If we look at the carbon one, we need 4 sig figs. So, Katie, what was after the 4.99?
5,
Okay, so we're gonna have to round up. So if I keep rounding up, the 9s becomes 10 and 10 and 10 and 10. So I get 5.000 for that one. Excellent. And then the hydrogen, we'll need 3 sig figs. Go ahead.
4.43.
Yeah.
The fourth moles, how do you feel about
Excellent. 4.44. Thank you. Get moles written on the units for each of these. Yeah, Ivy. Because I wrote too many, it should just have been 16.0 grams. Looking at the periodic table I was looking at before. Thank you. If you're looking at that one, we can get more precise. Okay, my next step is to find the most simple ratio. So, what should I divide each of these by? Bless you. 2.22, yeah. I'll start at the bottom. That gives me 1. 2.22. That gives me 2. Five divided by 2.22 does not give me quite as nice of a number. What does it give me?
2.27.
I'm gonna go with 2.25 because it makes life easier. So 2.25. What number will I have to multiply each of these by to get a whole number? Yeah, 4. Good, we can think of quarters. And multiply them all by 4. So I get 4 my oxygen and 8 for my hydrogen and 9 for my carbon. So I can write out my final formula as C9H8O4. And we would need a lot more information on organic molecules and what the molecular formula is before we could name this. So I'm not going to ask us right now to name this one. Organic naming has its own set of rules associated with it that are even more in depth than we've done so far. Any questions before we move on? Because I didn't have a nice whole number here. I had 2.25, and the 2 5s, to get them to a whole number, I would multiply by 4. Excellent. Any other questions before we move along? Okay, just a little bit more writing to do. So, the molecular formula is the number of each of atoms of individual elements present in one molecule. You've got that part written down. It can tell us both the molar mass and the percentage composition. And we can determine it either experimentally using a mass spec or a couple of other things. Okay, the last one, why does it matter? Well, it matters because each of these have the same empirical formula. Methanol, ethanoic acid, and glucose, when we get them to their lowest ratio, are all CH2O. But they're very different molecules. Glucose is a sugar. Ethanoic acid, that's vinegar. One of them would be very pleasant to eat. One of them, you don't just want to start chugging. Methanol is not like the methanol that we use up here. I don't have a nice thing to contribute methanol to in your normal everyday life, like ethanoic acid and glucose. Otherwise I would. It would poison you though. The other two are edible as long as they're dilute enough. That would poison you. We're not going to calculate the mass of each right now, but we would need to know the mass to determine the empirical formula. And I want to make sure that we have enough time to check out of the lab, so we are going to end there. I will podcast the last example if you want an extra example. It was just an extra example. So if you want an extra example, you can watch the podcast on YouTube. Jen, the